Infrared spectroscopy is one of the techniques you'll need to know about for this internal. Infrared spectroscopy enables you to identify the functional groups present in an organic compound. It works on the fact that different covalent bonds stretch and bend at different frequencies. If you know the frequency, you can identify the bond. In the middle of the screen, you'll find three animations. The first two are the bonds stretching, whilst the last one is the bonds bending. When infrared light is shone through a sample of an organic compound, some frequencies will be absorbed by the compound, whilst others pass through. The amount that passes through is measured as the percentage transmission. The percentage transmission you can find on the y-axis of this graph, whilst the wave number you'll find on the x-axis. The troughs are referred to as peaks, and these indicate the presence of particular functional groups. Here you'll find the spectrum of ethanol. You'll find that the bonds are stretching. Here you'll find that the OH bond has stretched, the CH bond, and then finally the carbon-oxygen bond. You are not expected to remember which peaks refer to which bond. In the internal, you are given a table of bonds and wave numbers. This is an example of part of a data table. In the internal, you will need to look at the spectrum and match the peaks with the possible peaks found in the table. It may not be possible to completely identify the compound. For example, if you have a peak at 1700, it could either be an aldehyde, a ketone, or a carboxylic acid, just as indicated here on the data table. Peaks are often referred to as being strong or weak, and broad or narrow. For example, in this green region here, you'll find a peak which is strong and broad. In this next example here, this is what we call a weak peak or trough. This final example, this is referred to as being a strong and sharp peak. If we start looking at the alcohols, alcohols have characteristic peaks. You will find a strong, broad peak which represents the oxygen-hydrogen stretch. You'll find this peak round about the 3500-3200 region. You will also see a peak or trough just next to that, just below the 3000, which is an indication for the region of the carbon-hydrogen stretch. It's also worth noting the absence of peaks. For instance, in this example here, there is not a peak round about the 1700 region, which means this compound does not contain a carbon-oxygen double bond stretch. Therefore, this compound cannot be a carboxylic acid. Here is an example of a spectra for a carboxylic acid. You will note that there is a peak here around about the 3000 region, which is in green. This indicates the presence of that oxygen-hydrogen stretch. You'll note here the peak at around about the 1700 region. This is for the presence of the carbon-oxygen double bond stretch. And also in this purple region here, you've got a peak at around about 1300, which is the stretch for the carbon-oxygen bond. Next, we'll have a look at an example of the amines. If you note in the green region here, there are two peaks around about the 3500-3200 region. These peaks indicate the stretches for the nitrogen-hydrogen bond. You will notice that there's two peaks because in the amines there's two nitrogen-hydrogen bonds. You'll see just around the 3000 region here, you've got a stretch indicating the presence of the carbon-hydrogen bond. You also have a peak here in the purple region, around about 1650 to 1500. This is representing the nitrogen-hydrogen bend, not stretch. In the yellow region here, around about 1200 to 1000, this is representing the carbon-nitrogen stretch. In our next example, we'll look at the aldehydes. The aldehydes have a strong peak just around here, around about the 1700, 1600 region. This indicates the presence of your carbon-oxygen double bond stretch. You've also got a peak here in the green section, around about 2800, 2700, indicating your presence of that carbon-hydrogen stretch. This one is due to the bond with the carbon-oxygen as well. So the stretch is for the carbon-hydrogen bond here. In our next example, we'll look at an ester. In the ester, you will notice, just like with the aldehydes here, you've got that common peak round about the 1700, 1600 region. That's indicating the presence of your carbon-oxygen double bond. Plus, you'll note in the purple region here, you've got a stretch round about the 1300 region. This is indicating the presence of that carbon-oxygen single bond. Lastly, if we have a look at the ketones, you'll be able to identify that familiar stretch round about the 1700, 1600 region, just like the aldehydes and the esters, which is indicating that carbon-oxygen double bond. Now in the internal, you obviously have to be able to write the information and the data that you've collected. This is an example of what you'd write down. So if we're referring to our last example of the ketone, you would say that there is a peak at around about the 1700 region, which indicates the presence of a carbon-oxygen double bond. This means that the compound could either be an aldehyde, ketone, amide, ester, acid chloride, or carboxylic acid. To narrow this down, you'd have to note the absence of some of the stretches. So the absence of a double peak at around about the 3400, 3250 region, which would represent the nitrogen-hydrogen stretch, means that it cannot be an amide because it's not present. The absence of a wide peak at 3000, which represents an oxygen-hydrogen stretch, means that it cannot be a carboxylic acid. It cannot be an acid chloride, as there's not a peak at 850 to 550. This would represent the carbon chlorine stretch. In the internal, you should try and include at least 3 pieces of evidence from infrared spectroscopy in order to justify your choice of compound.